So as with derivatives, there are some properties that make life more simple. One is that if you take a function and multiply it by constant and then integrate it, you get the same as if you just integrate it and then multiply by the constant. So this is here illustrated by, we have a function f here, and then there's a function here which is 4 times f, right? It's just same function multiplied by 4. And it turns out that the area below 4 times f, as you see here, is the same as the area between below f here times 4. We just scale everything up 4 times. It doesn't matter whether we integrate like this and multiply by 4, or we multiply by 4 and then integrate. The next property tells us that if we have two functions, so here we have an f and we have a g, then if we add these two functions, getting this blue function here, then what do we get? Well, we get a new function. It's, if the two functions here are integrable, then so is the sum. And the area here is the same as the area here below this plus the area here below this function. So in other words, we can calculate the integral of a sum of functions by just integrating the functions individually. Of course, both of these results follow directly from the fact that integration and differentiation are related, right? We can see that exactly the same rules apply for differentiation rules. Right? So here comes a last rule, second to last rule, which doesn't have any analogs in the theory of differentiable functions. So here we take some value c, which is strictly between a and b. So here's a, here's b, and then we have some c in between. And then we see that taking the integral of the function f from a to b, from here to here, is the same as first taking the integral from a to c, and then taking the integral from c to b. So this whole area here is the same as this area to the left plus this area to the right. It's also geometrically quite obvious. And lastly, we have this inequality, which tells us that f of x, if f of x is smaller than g of x, for all x's in the interval we're looking at, then the same inequality holds for the integrals of the functions. In other words, you can see here that f is strictly smaller than g, right? Then we can conclude that the area below this function on this interval is less than the area below this function on the same interval. Again, it's quite obvious geometrically.